welcome to this explainer. Today, we are cracking wide open one of the absolute coolest topics in Class 10 math, triangle geometry. And hey, don't worry, we're going to do this entirely without getting bogged down by all that dense mathematical jargon. We're keeping it incredibly easy to understand. So let's just dive right in, shall we? By the time we wrap up, you're literally going to be a master of geometric shapeshifting. You'll be able to look at one of those terrifying textbook problems and instantly spot the simple visual clues hiding right in plain sight. Okay, to kick things off, I want you to think about something you probably do literally every single day. Have you ever just pinched the screen on your smartphone to zoom in on a photo? Right? Think about what actually happens when you do that. You're resizing the picture, maybe scaling it up to catch a tiny detail, or scaling it down to see the whole shot. But crucially, scaling the image up or down doesn't actually distort the picture itself. Like your friend's face doesn't suddenly stretch out of proportion. Everything stays exactly the same, just at a different size. Well, that simple, everyday concept, that is the entire foundation for what we're exploring today. Now, let's tackle a couple of terms that textbooks absolutely love to throw around, and let's just translate them into plain English. The first one is congruence. If two shapes are congruent, they are identical clones. I mean, exact same shape, exact same size. If you slid one on top of the other, they'd match up perfectly. But when you take one of those shapes and you simply resize it, just like zooming in on your phone, you create what we call a similar figure. So the big crucial point here is this. Similarity means the shapes are exactly the same, but the sizes are different. It's essentially just a scaled version. Now, you know mathematicians, they absolutely love their shortcuts. So instead of writing out is a proportionally scaled version of every single time they want to talk about this, they use a symbol. You see that wavy little tilde symbol? That squiggle is basically the math world's shorthand cheat code. Whenever you spot that symbol sitting between two triangles, boom, you instantly know the secret. One of them is just a zoomed in or zoomed out version of the other. So the golden rule that kind of holds this whole thing together is actually really simple. If one triangle is just a zoomed in version of another, what actually changes? Well, the outer borders, the side lengths, they shrink or they grow. But here is the absolute magic key. The inner angles are locked perfectly in place. Think about it. If you have a triangle with a 90-degree corner, no matter how massive or microscopic you make that triangle, that corner is always going to remain exactly 90 degrees. Right, so how do we actually prove two triangles are similar without having to physically pull out a ruler and measure every single inch of them? Well, we use mathematical cheat codes, which the textbooks call criteria. If we know just a few specific pieces of information match up, we can guarantee that the rest of the triangle is perfectly scaled. Let's break down the most popular criteria so you can easily spot them in the wild. Let's take our very first cheat code, the SSS, or side-side-side criterion. Take a really close look at the numbers on these two triangles. On the smaller one, we've got sides measuring 2.5 and 5. On the larger one, the sides are 5 and 10. You see it, right? Every single side of the larger triangle is just a perfectly doubled version of the smaller one. Because all three sides share the exact same scale ratio, in this specific case, they're all just multiplied by 2, we know for an absolute fact that these triangles are similar. We literally don't even need to measure the angles to know that. Moving on, our next rule builds right on top of that, the SAS, or side-angle-side criterion. So imagine you've got two sides that are proportionally scaled. Now look at the angle wedged right between those two sides. If that shared, squished-in angle is exactly the same in both triangles, like an 80-degree corner, let's say, it physically forces that invisible third side to scale up perfectly too. Because you've locked that angle in place, the entire triangle is locked into similarity. It's pretty neat, right? Okay, the final cheat code is honestly, arguably the easiest one to remember. AAA, or angle, angle, angle. Remember our golden rule from earlier? Similar triangles have the exact same angles, period. Well, it naturally follows that if you know all the angles match, you have guaranteed similarity. And here is a super fun shortcut for you. Because all the angles inside a triangle must always add up to exactly 180 degrees, if you know just two of the angles match, the third one is physically forced to be identical. Finding just two matching angles is totally enough to solve the puzzle. It's like getting a mathematical 2-for-1 deal. All right, now we're going to tackle something that has a really intimidating textbook name, the basic proportionality theorem, or sometimes it's called Thales' theorem. It sounds like a total headache, I know, but I promise you it's beautifully simple. Keeping this entirely to easy to understand language, you don't even need to stress over that formal name. All it actually means is this. If you take a triangle and you draw a straight line right across the middle of it that is perfectly parallel to the base, you've just created a mini triangle sitting right inside the top of the big triangle. And guess what? That mini triangle is completely, perfectly similar to the big one. See that dividing line, DE? Because it's perfectly parallel to the bottom base BC, it acts kind of like a neat little slicer. It cuts the left side of the triangle and the right side of the triangle in the exact same ratio. So if the top left chunk, AD, is exactly half the size of the bottom left chunk, DB, well then the top right chunk is also going to be exactly half the size of the bottom right chunk. The proportions on the left perfectly, flawlessly mirror the proportions on the right. Now I know, if you crack open your math textbook, you are highly likely to see a visual setup that's just totally full of perpendicular lines, right angles, and a bunch of complex algebra, just like this, in order to formally prove the theorem. But I really want to reassure you here. While the algebra is the engine under the hood making the math actually work, you don't need to memorize the engine to drive the car. Just keep your focus on the core visual concept. A parallel slice creates perfectly mirrored proportions on both sides. You know, math also really loves a two-way street, which brings us to the converse of the basic proportionality theorem. Now, converse is really just a fancy academic way of saying that the rule works in reverse. If you measure the sides of a triangle, and you happen to notice that a line has sliced the left side and the right side into identical ratios, boom, you instantly know that slicing line absolutely has to be perfectly parallel to the base of the triangle. It's the exact same puzzle, we've just solved it backwards.
So how do we actually take all these shape-shifting rules and, use them? Basically, you treat them like you're a geometric detective. Step 1, look at your problem and figure out what clues you actually have to work with. Do you have side lengths or do you have angles? Step 2, pick your cheat code. Does your evidence fit the SSS, SAS, or AAA criteria? And finally, step 3, once you've proven they're similar, you just set up your scale ratio to find whatever piece is missing. Let's actually see this in action.
And I hear you asking, why does any of this matter outside of a math classroom? Well, these rules actually allow us to measure things that are physically impossible to reach. In the source material for today's explainer, there are some pretty classic problems, like calculating the length of a shadow cast by a massive 6-meter vertical pole, or figuring out the shadow of a 90-centimeter girl walking away from a really tall lamppost. Now, you obviously can't easily measure the light coming down from the sky, unless you have a remarkably tall ladder handy, but with similar triangles, you don't even have to. Because here is the truly brilliant part. The sun's rays hit the tall lamppost and the shorter girl at the exact same angle, and that means they naturally form two similar right-angled triangles. You have one massive triangle for the lamppost and one mini triangle for the girl. Because we already know they're similar, we just set up a super simple fraction. The height of the lamppost divided by its shadow is going to equal the height of the girl divided by her shadow. You just match the ratios, multiply it out, and you instantly have your answer. I mean, it's practically a math superpower. And honestly, there you have it. You have successfully navigated the core rules of similarity. You've tackled the SSS, SAS, and AA criteria, and you even conquered the basic proportionality theorem, all by just understanding how to visually scale a shape up and down. You now have the tools to break down super complex problems into really simple visual proportions. You've traded confusing formulas for the simple art of visual shapeshifting. So I'm going to leave you with this one thought. If you can master the simple art of geometric shapeshifting, what other complex math mysteries are you ready to absolutely unlock next? Thanks so much for joining me on this explainer, and hey, keep that curiosity sharp.